So we're going to jump into lesson 10.1. So we just finished chapter 6, and we're actually going to jump all the way to lesson 10. And the reason we're going to do that is because we feel that this next unit really fits well with everything we were just doing. So there's no reason to wait. Let's jump right in so we can see the connection and use all the skills that you just had in chapter 6 right here in chapter 10 to help us solve systems. Now, this is one of the most important parts of algebra, something that you will see moving forward. You'll see it on the SAT. You're going to see it in all your math classes moving forward. You have to be able to solve a system of equations. It's one of the big key things that you have to have when you leave algebra is know how to do this. And you should have touched on this in middle school, mostly in Math 8. Okay, so this shouldn't seem completely new. But the big idea is we're going to solve a system of equation, and that means finding all the solutions that are common to the equations. Common means the same. So a system is a set, so meaning multiple, set of equations or inequalities, and they're joined by the word and, meaning that they all have to be true, that together describe a single situation. Okay, so two things have to be true at the same time. That's a system. So it's not just one specific equation that needs to be true. Two equations, both referring to the same situation, and a system is where both of them are true. So the solution to the system, we're going to write as an ordered pair, so like a coordinate point, or x and y, that satisfies both equations or inequalities. So if I take the x value and the y value that I get as my answer, and I plug it into both equations or both inequalities, it's going to make both of them true. So you could have two equations or two inequalities and find the solution to one of them, and every equation is going to have multiple solutions. If you think about a line, every point on that line is a solution to it. So every line, every equation has a ton of different solutions, but not all of them are going to match both equations in our system. So what we're going to do is try and find what's the point, or where are the multiple points that these equations kind of overlap, and that's what they're visually going to do on a graph. But where do they have, or where do they share the same solution? Where do they have the same point? And that's going to be the solution to our system. So system just means you've got multiple equations. The solution is going to be the one point, or it's possible to have multiple points where these overlap and they have the same numbers for x and for y. Now, it is possible that there's no solution, and we've talked about these types of situations before, but that is referred to sometimes as the empty set. So you're going to refer to your answers as a set of numbers. And so if it's an empty set, there's no numbers there because there's no solution. Or the null set, that's probably a new term. And when we write that no solution, that actually, technically, we call that the null set. Okay, and this is your empty set. So what this is kind of some brackets here. And traditionally, if there's an answer, the answers are going to be listed inside of these. They look like parentheses. And so if there's nothing inside of them, it's an empty set. There's no answers, or we write no solution, and this can be referred to as the null set. Now, there's multiple ways, like I kind of just dove into, of writing a solution here. So here's some of the various ways, and the way we're going to focus on the most is just your ordered pair. That's what we're going to do, but you can write it as an ordered pair identifying the variables. So just writing x comma y equals and then replacing it. Now, most of you would say, well, why would I write that extra part? Why can't I just write this? And you can, but just know that sometimes you'll see it written like this. You can also do it individually. So we know x is 14, y is 9. So you can actually write that out, x equals 14, y equals 9, instead of plugging into an ordered pair. And you can talk about the set of ordered pairs. Now, in this case, there's only one solution. So here's those brackets that you see. And inside are all the possible answers. Now, in this case, there's only one ordered pair in there. It is possible to have multiple ordered pairs. Okay, so that can change based on the situation. You can have a bunch of stuff inside that bracket. All right, we're going to look at example number 1. We're going to consider this system. So we've got two separate equations. We could come up with some numbers that we could plug into the first one. For instance, if you just plugged in 0 for x, you could find out what y is. Or if you plugged in 1 for x, you could find out what y is. If you plugged in 10 for x, you could find out what y is. And all of those ordered pairs that you're producing when you do that, those are all solutions to this equation, which would be on the line if you put it on the graph. But they're not all going to work here. So if I plugged in 0, I'd get 0, 0 minus 7 is negative 7. So the point 0, negative 7 works for this first one. But if I plug in 0 and negative 7 for x and y in the second equation, 0 goes here, 7 goes here, 2 times 7, I don't get 10. It does not work here. So the point 0, 7 is a solution for the first equation, but not the second. And what we're looking for is the ordered pair that solves both of these. And that's not always so easy to find. Okay, so what we're going to do first, before we talk about how do we do this by graphing it and finding the solution, we're just going to look at two different ordered pairs and test to see if they are solutions, because we need to make sure first and foremost that you understand what the solution actually means. So it's got to work for both of these equations. So we're going to verify that this ordered pair is a solution to this system. So that means we're going to take x equals 6 and y equals 11, and we're going to plug it into both of these equations, and we're going to see if it works in both of them. So starting with the first one, y equals 3x minus 7. I'm going to go ahead and plug in my 6 for the x and 11 for the y. So 11 equals 3 times 6 minus 7. So I'm going to get 18 minus 7. It's kind of like a check from back in the day. And you're going to get 11 equals 11. So 6, 11 is a solution to this equation. But is it a solution to the system of equations, which just means both of these equations? So now we need to go test it in the second one. And so we're going to take 2y minus 2x equals 10, and we're going to test it with the 6 and the 11. So 6 goes in for x, and 11 goes in for y. So 2 times 11, and 2 times 6. So I've got 22 minus 12 equals 10. I get 10 equals 10. And so this ordered pair of 6, 11 worked for the first equation. It also worked for the second equation. We got a true statement. So we have verified that this is true. So we can say, yes, 6, 11 is a solution to the system of equations. Six 11 is a solution to the system of equations. So on the flip side now, we're going to take a look at this one. We're going to show that 1, negative 4 is not a solution. So x equals 1, y equals negative 4. Show that this is not a solution. So we're going to go again right back to where we started using these two equations. So y equals 3x minus 7. And we're going to plug these in. 1 for x, negative 4 for y. I'm going to multiply, I get 3 minus 7. And I'm going to get negative 4 equals negative 4. So it worked right there. So 1, negative 4 is a solution to this equation. But is it a solution to the system of equations? We don't know that until we try it in the other equation and see if it works. So you can kind of guess that it's not going to work. So let's take a look. Plugging in 1 for x and negative 4 for y. We're going to get negative 8 minus 2. And what do we get? We're going to get negative 10 equals positive 10. Well, that's not a true statement. Okay, so we're going to say no. 1, negative 4 is not a solution to this system of equations. All right, and we will tackle how do we find the answer when given these two by graphing on the back, and you can go to the next video for that. All right, so here in part 2 on the back of 10.1's notes, we're going to use a graph to help us solve a system of equations. So on the front, we were given some points and we tested them to see if they were solutions to the system, and if they were, they worked in both equations, not just one. And for most of these, there's either going to be no solution at all that works. These lines never cross, and we'll see what that looks like. Or, more likely, there's only going to be one specific solution. Because remember, these equations form lines on your graph. And most of the time, lines only hit in one spot. They're going to cross once, and then they both go their separate ways forever. So for most of these, there's just one single solution. All right, so we're going to take these two and we're going to graph them, and we're going to see where do they cross. Remember that the lines on the graph represent every single solution. Every point on those lines is a solution for that specific single equation. And so if they cross that one spot that they share, that point is the solution that works for both equations. So all we have to do is put these on the graph and see where they cross. It's actually pretty easy. So if we have this equation, y equals x, I want you to think about what the slope is, what the y-intercept is. So the slope's whatever's in front of x. There's actually a 1 there. So the slope is 1, which is the same as 1 over 1. So we're going to be going up 1 over 1. And our y-intercept, I don't have a plus or a minus, which means that my intercept is 0. So if I go over here to put this line on the graph, I'm starting at the y-intercept of 0, which is the origin right in the middle. And I'm going to use my slope of up 1 over 1. And my line's going to look like this. Now, because we're trying to find one very specific point that these cross, we can't just draw a quick line and not have it actually be straight and follow everything. So if you want to use a straight edge, that's fine. Or draw every point that you can and make sure that this line hits all those points. Because we don't know where this next line is going to cross this one, or if it is at all. And so if you just draw it and your line happens to curve off, and that's where they're supposed to cross, then you're not going to be able to see the point that you need to see. All right, starting with the next one. So we have 4x minus 2y equals 12. We want to put this one on the graph, right? And so we can't do that until this is in nice y equals form. We just kind of tested on that, and that's why we're doing this after chapter 6. So we want to get this into y equals everything else. Y equals mx plus b form. It's going to make our life easy, giving us the slope and intercept. So first thing I'm going to do is I'm going to move this x away from y. So I have negative 2y. I'm going to put the x in front. So negative 4x, 12 is positive, plus 12. Get rid of this negative 2 by dividing everything by negative 2. It's not an inequality, so I don't have to worry about flipping anything. So y equals, two negatives make a positive. 4 divided by 2 is 2. And a positive and a negative make a negative, so I write minus. 12 divided by 2 is 6. Okay, so my slope is 2, which is 2 over 1, up 2 over 1. My y-intercept, minus 6, is negative 6. So that's where it's going to hit the x-axis. And so if I go to, the y-axis, negative 6. So if I go to negative 6 on the y-axis, that's where this line starts. Always start at your intercept. And then use your slope to draw the rest of the line until it hits this one. Okay, so it's going to go up 2 over 1 because the slope is 2. Up 2 over 1, up 2 over 1. You can see it's not going to hit it for a while. Up 2 over 1, up 2 over 1, up 2 over 1. And it doesn't hit until right here. So you can draw that line, really focusing on where it's going to cross. Now you're not done. We need to actually identify the solution. So what point is this? Okay, and so the x value is 6. And the y value is also 6. So that point that they cross is 6, 6. There's only one solution here because it's the only one spot that they cross. That solution is 6, 6. And just like we did on the front, if we took this now and we went back and plugged it into both equations, it would work on both sides. You'd plug it in here, you'd plug it in here, 6 and 6. You'd get 12 on both sides. If you put 6 and 6, you get that. And any other point that you see on either one of these lines, it's only going to work for that line, not the other one. The only point that satisfies this system of equations is 0.66. It's the only x and y value that will work. Okay, so let's look at some different situations. Now that's your standard one that's going to cross once. Here's a different one. So if I have y equals negative x plus 4, my slope is negative 1. That's negative 1 over 1. So that's down 1 over 1, down 1 over 1. And my y-intercept is 4. So I'm starting at 4. That's where it hits the y-axis. And now I'm going to use this slope of negative 1, 1. So down 1 over 1, down 1 over 1, all the way across this graph. So it looks like this. And let's see what happens with the other one. So y equals negative x minus 2. What do you notice right away? The slope is also negative 1, which means when the slope is the same, it's going to move across the graph in the same way. It's going to go down 1 over 1, down 1 over 1, down 1 over 1. And so if they're both going down at the same rate, that tells you something. Okay, we'll take a look at it in a second. Y-intercept is negative 2. So we're going to start at negative 2 on the y-axis. That's your y-intercept. And we're going to use our slope. Down 1 over 1. Over and over and over. And if you can start to visualize this, if it is going down at the same rate as the other line, if the slope is the same on both of your lines, they're going to run exactly the same, and they are never going to cross. So there is no solution here. These two lines are parallel, and so it's important to understand same slope means parallel. All right? Because they're going to run down or up, whatever it is, the same amount, so they're never going to cross. They're going to run side by side if they have the same slope. Now there's one more special solution. Okay, I want to look at it on the last one. So starting with y equals 2x minus 5, that's in beautiful form. So our slope is 2, our y-intercept is negative 5. So let's throw that on the graph real quick. We're starting at negative 5. Slope's positive 2, which is 2 over 1, up 2 over 1. Okay. And now the other one, we got to do a little bit of work too. It's not in good form. So we got to get y by itself, move the x first. So I have negative 3y. I'm going to put the x up front, negative 6x, positive 15. I put plus 15. Divide by the negative 3 all the way across the board. So y equals, 2 negatives make a positive. 6 divided by 3 is 2. Positive and a negative make a negative, so I'm going to put minus. 5 divided by 3 is 5. My slope is 2. So right away, look, I've got the same slope. So your first instinct might be to say, oh, there's no solution because they have the same slope. They're going to run the same direction. They're never going to touch. But take a look. The y-intercept is exactly the same as the y-intercept here. These are actually equivalent equations. So when I go to put this one on the graph, I'm going to start at my intercept of negative 5. And I'm going to use my slope up 2 over 1, up 2 over 1. And every single point is going to fall on this line. And so any point that's on this line is also going to be on this line. And you might say, well, it's just the same equation. So this isn't really a system, right? They're the same equation. They're not different. But in a real story problem, these may represent different things. Okay, and that's why they're written differently. But we come to find out that they actually have the same set of solutions. And so what we're going to say is there is an infinite number of solutions. Now, what you can't go and say is you can't go and say all real numbers. Now, we use that a lot before, but we can't say all real numbers because there's numbers out here that are not going to be the solution. Okay, so infinite solutions is the proper term that we're going to use.